Okay, welcome back to the workshop. It's the last day today, and I know that some people have already left us, but thank you for the ones who have stayed for the entire week with us. Our first speaker today is Mingda Qiao. He is an assistant professor at UMass Amherst, and for years he's been thinking and working on federated learning from a very principled theoretical perspective, and we're going to hear from him about collaborative platforms for collaboration.
Thanks for the introduction and thanks for inviting me. So this is joint work with Mingda and He, both here at Berkeley. It's on platforms for efficient and incentive-aware collaboration. So the entire theme of this program, federated collaborative learning, is about collaboration. So in federated learning, the users, the devices are sharing the data, collaborating, so that the server to learn a more powerful model than what could be trained on each individual user's data alone. And from a more learning theoretic point of view, there's a model called collaborative path learning, which similarly, a centralized learner is drawing data from different agents so that they can train a more accurate model or accurate personalized models than what in a more sample efficient way than solving these n learning tasks independently. So in any collaboration, there are at least two important desiderata. So one thing is the social efficiency. We want to minimize the total cost or total work incurred by the participants. And in fact, that's the whole point of collaboration. But also important is the incentive of individual participants. We don't want them to leave or deviate or ruin the collaboration in some sense. And we'll see very soon that these two desiderata can be competing, even in very simple models of collaboration. But before I go on, I should mention this is not unique to learning scenarios. So there are early work in peer-to-peer systems, for example, BitTorrent, then notice this issue of free riding, which is a more general thing in collaboration. But for concreteness, I'll be focusing on this federated collaborative learning scenarios for concreteness. So roughly speaking, in such scenarios, there are n agents, and each of them wants to learn their own learning task. And these learning tasks might be related, but somewhat different. As you can imagine that each agent is just one hospital, and they all want to learn some automated diagnosis, but they're serving different subpopulations, which makes the data domain slightly different. Then in this context, we can model efficiency as the objective of minimizing the total amount of data, as long as we can solve all the learning tasks from all the agents in the end. And the incentive of each agent would be to minimize their own data contribution, because collecting and sharing data comes with costs. They want to do this as long as their own learning task should be solved accurately in the end. So this work is part of a very rich recent literature on incentives and fairness in federated collaborative learning. The closest to our work is this line of work on mechanism design to incentivize truthful data sharing and prevent free riding. And there are also other lines of work on encouraging participation, promoting fairness, and mechanism design for explicit for data markets. So from this long list, it's not very informative where our work situates. So another way to break down all these different models is look at the components of the model. So one thing is how learning is modeled in these frameworks. There are simple learning tasks like mean estimation, linear regression, for which the learning accuracy could be expressed in closed form. And there are also other work that focus on binary classification or use path learning bounds as a proxy for the learning guarantees. The second component is a model of attacks. A rather benign model of attack is free riding, that's just effort minimization. And related to this is to defect, which means the agent might quit the collaboration as soon as they receive an accurate enough model in a iterative or sequential learning scenario. There are more serious attacks behavior like fabrication, data poisoning, which we heard from Kirsty and Florian earlier this week. And this also what's called Sybil attacks. So those are creating false identities by duplicating or splitting your data set. And one more component is the role of the mechanism in this framework. So there could be no mechanism at all, in which case we just observe the hardness of collaboration. And the mechanism could also use monetary payments or penalties to change the utility structure of the agents. It could also penalize the agents by injecting noises or use some reputation system, which makes more sense in repeated or iterative learning scenarios. So with all these in mind, here's what is this work. We used this random discovery model of Blum, Hartlab, Phillips, and Qiao, which I will describe very shortly, which is a very simple model of collaboration. And the focus will be on preventing free riding or effort minimization. So that's a rather benign attack model. So we will not directly address fabrication or poisoning. And our mechanism is via Bayesian persuasion, which I'll also introduce shortly after. So it's a very clean model of how persuasion works in practice. And it's about how an informed party could persuade the less informed parties to take certain actions. So here's the plan. I will describe the collaboration network model and highlight a very high price of stability without a platform. I'll then take a detour to introduce Bayesian persuasion and then describe how it's used to enforce efficient collaboration. I'll end with a few open problems. So here's a model. We have an unweighted, undirected graph on the right-hand side. So it's a special case of this random discovery model of Blum, Hartlab, Phillips, and Qiao. So each node in this graph corresponds to one agent in the collaboration. We draw an edge between agent I and agent J if their learning tasks are related, meaning that agent I could benefit from the data shared by agent J and vice versa. So we're assuming the graph is undirected. This is a symmetric relationship. And then a configuration of the collaboration could be described by this vector theta, where each entry theta I is a number between 0 and 1 that specifies how much data agent I is sharing. So we're normalizing things. So we can think of this 0 as 0 data points and 1 as, say, a million data points. And with this in mind, what would be the amount of data that is available for agent I? So that would just be theta I, which is their own data, plus the sum of theta j for all j that is neighbor of I. So that's saying I can benefit from my data as well as all the data contributed by my neighbors in the graph. So is everyone with me on this? Good. So that's a one-line summary of the model. And then we can talk about feasibility and stability in this network. We say that this configuration theta is feasible for agent I if we have this inequality, which basically says agent I has at least one unit of data for their own task. So implicit in this assumption is one unit of data is sufficient and necessary for solving each learning task, and this is the same threshold for all agents. Furthermore, we say that theta is stable for agent I if the agent could not further decrease the value of theta I without sacrificing their own feasibility. So this basically says that theta I, the agent I's action cannot be unilaterally changed without changing feasibility. So let's work out a few simple examples. So if we focus on this graph on the right-hand side, we can verify that the top left corner, that agent, the configuration is feasible for them because they're getting 0.5 on their own. They get another 0.5 from the center node. So that's one unit in total. This also means that the configuration is stable for them because any deviation below 0.5 violates the feasibility constraint for them. We can also verify that the center node is unstable in this configuration because they are already benefiting from all the neighbors' data, like 0.5 there, 0.5 here. So they could just play 0 and free ride without violating feasibility. So let me do one more example of feasibility and stability here. So let's consider this double star graph, which is two center nodes connected by an edge. And for each center, there are n/2 - 1 leaf nodes connected to it. So what's one natural configuration of collaboration here? So one thing we should consider is we let the centers contribute 1 because they are very powerful. They are influential to all the leaves. And let the leaves free ride. So this is a configuration that is very efficient in the sense that we need n units of data if they were not collaborating, but now 2 units of data would suffice. But this is very unstable because if I were the center on the right, I might think I'm getting 1 unit from the left center already. I can just play 0 instead. So that's efficient but unstable. Yeah.
So do you have an example of this type of configuration, how it might arise in a learning task? Because this center node, it appears that its target distribution is like more diverse in some sense. That's why it seems to be benefiting from algorithms. But that other node, which is on the leaf, only cares about the center node, which would make you think that it actually also cares about a diverse target distribution. But then it doesn't care about the contribution from the other nodes. So
Yeah, that's a great question. So my understanding of the question is whether this graph could arise from like real learning scenarios, because it's not satisfying certain like triangle inequality. Like if these two nodes are connected, these two are connected, intuitively these two should also be connected. So that's my understanding of the question, and that's a great question. So this is not like explicit model in this graph, and towards the end of the talk, I would mention some alternative models. So the takeaway would be like, there are like maybe more realistic models for learning scenarios that inherits these type of examples, but in a more like complicated fashion. So the short answer is like, yes, this doesn't exactly correspond to a learning scenario, but such example still arises in those cases.
okay, in particular, like one thing I just wanted to add is like if someone really has a rare target distribution,
Yes.
versus someone which has like a very canonical target distribution, is it actually even clear who should be contributing more? In this model, the way dependencies are arising, it's not clear that the rare person actually needs to.
So my understanding was the question was like, so what's the like fair? What's the notion of like fair contribution from the?
Yes.
Yeah.
Some
So
equators.
yeah. So as long so far we're just like minimizing the total cost. So it's like assuming that there's a centralized party who could specify who contributes. So we're like just restricting our attention to like the social efficiency in total, but not the like fairness, other fairness notions. Thanks for the question. So let me move on. So there's one efficient and unstable configuration, but if we flip the things, let the leaves contribute and centers contribute 0, we get something that's very inefficient because the total amount is n minus 2, that's roughly n. But at least this is stable because you can see the leaves are on their own, they have no one to depend on, so they cannot deviate. And the centers are already free riding, so they cannot deviate at all. So with this example in mind, we could talk about the price of stability in this model. So we define two benchmarks. The opt is the cost of the optimal feasible solution. So that's the minimum of the sum of theta I, that's the total contribution, subject to feasibility constraint for everyone. And that's going to be 2 for the double star graph, as we just seen. Another benchmark is adding this additional stability constraint to it, which we call opt stable. So it's the same minimization problem with this additional stability constraint. And the claim is on the double star graph, this will be omega n, this is linear in n. So a few slides ago, we saw this stable configuration with cost n minus 2. We could be a bit more clever by flipping the configuration on one side. So we let the leaves free right here and let this center contribute 1. So that gives a slightly lower cost of n over 2. But you can't be more clever than this. So this, we have a linear in n lower bound in general. And then the price of stability is just the ratio between these two benchmarks. So that's the additional cost you pay by taking into account these incentives or stability. And that's going to be linear in n, even on this double star graph, which seems pretty simple.
Sorry, usually price of stability is about Nash equilibrium. Is your definition of stable equal to Nash equilibrium?
Yes, I think so. I think like this could be formalized like by specifying the exact utility function, and then I think the stability would correspond to basically equilibrium in that formulation. But like, yeah.
I think so too. I just was.
Yeah.
I mean, it's strange to see the phrase used out of the usual context.
Yeah, I think like one possible if you get deficiency in the data, you get some minus infinity utility, and then otherwise your utility is like your contribution. So you are trying to minimize your contribution subject to feasibility. That's one way of like setting the utility to make that like matching the usual terminology. And our claim is that this price of stability analysis could be overly pessimistic in a few ways. So one thing that was implicit in the analysis was all the agents know exactly what the graph is looking like and where they are in the graph. So what does this mean in the learning scenario? So this means that agent knows not only their own task, but also everyone else's learning tasks and how they relate to each other. So that's something each individual agent is unlikely to know in like realistic, say, data sharing or data exchange situations. Also, we know that the mechanism or the platform is not doing anything in this analysis. So in principle, like these data sharing and could be happening on data marketplaces or data exchange platforms, and the platform could gain more information about the metadata of the learning tasks. So to reuse the fact that the platform might have more information about the graph while the agents don't know the graph, so that the platform could use this information advantage to steer the agents into efficient collaboration. So that's the question we asked. So to answer this, I'll take a detour and introduce like Bayesian persuasion. So how many of you have heard the term Bayesian persuasion before? Okay, so I'll just be quick and give a very short toy example. So let's say someone is writing a red letter for a job candidate. And for simplicity, the letter is just a bit of information, strong or weak. And the candidate could be above the bar for the position or below the bar. And each happens with a prior probability of 1/2. This exact fit is something known to the letter writer, but unknown to the company. So what the writer tries to achieve is to send a signal to the company to persuade the company into hiring the candidate. And more exactly, we're assuming that the candidate will get hired if the perceived probability of them being above the bar, conditioned on the signal in the letter, is at least 2/3. So it's saying the company is not willing to take a chance, and as long as there's some predominant evidence suggesting that the candidate is a good fit, they will just hire. And the objective is to maximize the overall probability for a candidate to be hired.
When you say fit known to the letter writer, what is fit?
Fit is just above the bar or below the bar.
Oh, okay.
Yeah, thanks for the question. Yeah, so again, a two-line summary of the problem. And what would be a truthful strategy here? You just write a strong letter for candidate above the bar. In that case, given the letter, the company knows the fit, and the candidate gets hired if and only if they were above the bar. So the overall probability will be just 1/2, the prior probability. But here's a more strategic behavior of the writer. They're going to write a strong letter if it's above the bar, which is intuitive. But otherwise, they just flip a coin and write a random letter. And the claim is, given a weak letter, we know for sure it's from the second case, so no higher. And given a strong letter, the posterior probability will become 2/3, which exactly matches the threshold and leads to a higher. And I'm going to show you this claim without doing a lot of math. So we can imagine this rectangle depicts the range of all possibilities, where the left-hand side is when the candidate is above the bar, and the right-hand side is for below the bar. So those two are of the same area. What the letter writer does is to divide the space using this division and write a strong letter for the possibility on the left-hand side. And this exactly matches the strategy here, because you get a strong letter if you were above the bar in this shaded area, and you get a strong letter with probably 1/2 otherwise. And then from this picture, it's pretty clear that conditioning on a strong letter, which means we restrict our attention to what's on the left-hand side of the division, the posterior probability of above the bar becomes 2/3. It's also clear that the overall probability of a higher, which is the overall probability of a strong letter, is 3/4, and it's strictly better than the truthful strategy. So this is just a toy example showing that when you hold more information than someone else, you can send signals in a strategic way to persuade them into certain action of your preference. And as I described this example feels like a trick or even unethical in some sense, but I'll show you how this Bayesian persuasion should be applied to our collaboration scenario and leads to efficient collaboration. So let me give a few more details about the model. So we said that we assume the agents don't know where they are in the network. And more exactly, we assume that they are mapped to the nodes via a random permutation chosen uniformly. So this distribution is something known to the agents, but the exact realization of the permutation is known to the platform, but not the agents. And recall that our question was, can we use this asymmetry in the information so that the platform could use Bayesian persuasion to enforce efficient and stable collaboration? Yeah.
Is the graph structure known?
Yeah, we're assuming that the graph structure is known to the agents, which is theoretically it's without loss of generality because you can send the graph as a part of the signal in the end. And so we're going to use this private Bayesian persuasion formulation, which is a generalization of the toy model into multiple receivers. So some platform is sending signals to multiple receivers independently, private channels, and each receiver will look at the signal and do some posterior updates. And let me be more specific of what's happening. So first of all, the platform is going to observe the realization of the permutation. And then they will choose a vector of signal. So signal SI is a number between 0 and 1. It's a message sent to agent I. So the way to view this is SI is the recommended action for agent I, or recommended data contribution for agent I. So far, this doesn't say anything. It's not really if you receive a signal of 1, you might wonder, should I just follow it, or should I do something else? So this only makes sense if the stream is persuasive, meaning that whenever you receive a signal of alpha, your best course of action is to follow the recommendation and play alpha, or contribute an alpha amount. So mathematically, this corresponds to this condition, which says for any alpha between 0 and 1, it should equal to this minimization problem on the right-hand side. So what this achieves is you can think of the agent receiving alpha. So they're wondering what would be the best alternative action alpha prime, which is non-negative. They want to do this as long as playing alpha prime satisfies feasibility in expectation, which means their own contribution alpha prime plus all the external contribution should be at least 1. But what's important here is that this signal of alpha is going to change the distribution a lot. So this expectation is a conditional one. So what's really happening is there's a distribution of the permutation, and also a distribution specifies how signals are chosen. And given this exact signal, I'm going to update my posterior belief of where I am in the graph, as well as what my neighbors are going to contribute. And all those factors lead to this conditional expectation. So the assumption here is that the agent computes this expectation and somehow best respond to this expectations by playing the minimum alpha prime so that this feasibility is satisfied in expectation. This question?
Could you clarify, so the agents know the structure of the graph, they just don't know where they are in the graph?
Yeah, that's right. The agent knows the graph, but not the exact permutation. Yeah, please.
Satisfying the condition and expectation doesn't seem like it is consistent with your previous model.
Yeah, I'll mention this at the end, but what's implicit in this is that they are using some quadratic loss or negative quadratic utility as a utility function, so that given a distribution over.
So previously, when you said what utility model would you put on the game, you said negative infinity for infeasibility, and now you want to change that to some quadratic utility?
I think that quadratic utility is also going to give the same behavior in the previous formulation, because you're going to respond in a way so that your contribution plus the external contribution matches 1. So more exactly, the utility is like your contribution plus external contribution minus 1 squared and the negation. So that's going to lead to exactly the same behavior as I described in a few slides ago.
Okay, sounds right. I'd rather have one model, though.
Any decrease in utility work for the previous part? I mean, if the contribution decreases,
I think for the first part, this is true. And for this part, what's implicit is given a distribution over external contribution, what matters is the expectation. So that's kind of implicit in, or like, that's what the definition says. And one example of achieving that is through this like quadratic kind of loss. But definitely there are like other refinements of the utility which might make more sense by like modeling the asymmetry in the like, punishment on both sides.
So there's the data of the people,
Yeah.
but the graph is also, their position on the graph is also a kind of data. And so this, it seems like we're assuming that the data about the graph is very expensive compared to the data about that they're collecting. Because otherwise they could figure out where I'm on the graph and then cheat the mechanism.
Yeah, exactly. So our assumption was like everyone holds their own data, but they don't know much about what the other people's data. And that kind of metadata is something exclusive to the platform. So that creates the possibility of like using this asymmetry in information.
But they don't, in particular, they don't know anything about where they're on the graph.
Yes.
Maybe that's important. On the model or not?
And sometimes it's not about whether the data is expensive or not. Like, it's two different types of data you need. So if I want to know if my data and your data, like our sample sets overlap, it requires us to look at our marginal distributions and see if they overlap. And I would have to do it for everyone. That is how you would get to know where you're in a graph. So that is something that the platform has a lot more access to because it actually holds the data. But the part which is more about actually doing the effort, it's more like being able to know the label given your data set, which is definitely something that only you know and not necessarily anybody else. So it's like, it's not so much about expensive, more about these are very complementary types of information. And one is definitely available to the platform and other
Yeah, but in the real world, there's some price, right, that you could put on this only available to the platform data, and then you could trade them off.
but I'm not sure if that's true.
So within this model, we could revisit the double star graph that we just saw. So here's a very simple signal stream that like improves the performance on the double star graph. So we choose parameters p and epsilon, so those are very small numbers. So with a high probability of 1 minus p, I'm going to send 1 minus epsilon as a signal to the two agents who correspond to the center nodes. And I'm going to send signal 0 to all the other agents who correspond to the leaves. With the remaining probability, so this like reminds you of like this efficient but unstable configuration that we saw earlier. And with the remaining probability p, we do the opposite by sending 1 minus epsilon to the leaves and zeros to the centers. So again, this mimics the configuration that was stable but inefficient. The claim is, by randomizing this and choosing parameters carefully, so if we choose both of them on the order of 1 over root n, the resulting signal stream will be persuasive.
I thought the randomization was which node you were in the graph.
So there are two levels of randomness. So one thing is the permutation, but the signal stream is also like using randomness. So, so this like describes like given the permutation, what the signal stream is going to choose. So like the posterior update
So
depends on both.
This easy fact is taking expectations over the permutation too?
Yes. So the easy fact is just a verification of the aforementioned persuasiveness definition.
I mean, it looks like it doesn't need the permutation to be true.
Like if you know exactly where you are in the graph, like if you know I'm a center, or like this makes more sense if I like prove this like qualitatively, and maybe this makes more sense. So suppose you are someone that receives 1 minus epsilon. So what's your thought process? So you might be, in this case, that you are a center, and you get this configuration. In that case, you get a lot of surplus in the data because you have a neighbor who's also playing 1 minus epsilon, if they follow the recommendation. But there's also a chance that you are a leaf here, and the signal stream happens to use this configuration. And in this case, you have a deficiency in the data because you play 1 minus epsilon, you're not getting anything. And what the claim, or what the fact achieves is to balance this surplus and deficiency so that you don't, you have zero expectation. So you're going to follow this recommendation. So going back to your question, without this randomness in the permutation, if you know you are a center, you won't have this mixture of the two possibilities, and that's not going to work out in a similar way. So assuming this fact, we could just calculate the expected cost of the resulting stream, which is defined as the expected total contribution, and it's going to be on the order of O root n. And recall that without the platform, the price of stability was omega n, so we're kind of improving the cost from linear to square root. So the main result of our work was that this is not a coincidence for the double star graph, but it's something more general for any unit weight and undirected graph. So on any graph, we could achieve a cost of opt, the optimal feasible solution, times a O root n factor. So this generalizes the result from the previous slide. And there were a few, and one way to view this was the price of stability was as high as omega n, but we showed that through signaling stream, the POS can always be reduced to O root n in some sense. This is informed because this is not price of stability at all, but some approximation ratio. And we have a few bonuses. So first of all, we showed that this root n is tight. It's even tight for double star graphs. So on that specific graph, we could not do anything better than the streams that I described. And secondly, we generalize this to weighted graphs. So what I mean by weighted graphs is that, so in the graph, so between my node and your node, there might be an edge with weight, say, 1/2. And that basically says that each of my data points is worth half of a data point for your own task. And this model scenario where the tasks might be overlapping or have certain similarity between 0 and 1. And for that general case, we showed a sublinear POS improvement and a slightly better improvement if we made additional assumption on the edge weights. And all these results are of a worst-case analysis flavor in the sense that we showed the ratio could be O root n on any graph, and there is some graph where the root n is unavoidable. So what about instance optimality? We have a third result that does something of this form. So what we showed was on any graph where opt is strictly lower than opt stable, meaning that stability comes at a non-trivial cost, we can achieve a cost that's strictly lower than opt stable. And another way to view this is whenever the price of stability is strictly higher than 1, we could use signaling stream to get a new POS that's strictly better than the original one. So let me give you a very brief sketch of.
Can I ask a question?
Yeah, sure.
I think two things are happening in the signaling scheme. One is you have a signaling scheme,
Yes.
and the other is you have an assumption on the random permutation.
Yes.
And I wonder if you need both of these, or if only one of them is sufficient for these any of these upper and lower bounds.
I see. So if we don't have the permutation, everyone knows where they are in the graph, then my claim is that signaling is not going to work because once everyone sees the recommendation, you might.
We're talking like a correlated equilibrium now if you get recommendations.
Yes.
And you change the model to be this expected utility.
Yes.
And it's not clear that the set of correlated equilibria is equal to the set of Nash equilibria.
I see. Now I got your question. The question was whether we can achieve similar results without the assumption of the permutation by using correlated equilibria. I recall that we have a negative result of that form, but I don't recall right now. Let's discuss this offline. Does that sense? So let me briefly present how we prove this result. It uses some elementary graph theory. So what we do with the graph is we first identify a dominating set of the graph, which we call ds. And the purpose of this choice is that it's very similar to the opt, because the definition of the optimal benchmark is like a linear relaxation of the dominating set. And this mimics a situation where the configuration is efficient but unstable because it has a cost that's more or less optimal. But there might be internal edges or induced edges between the dominating sets, and that causes instability. And after doing this, we're going to remove this dominating set from the graph and choose a maximal independent set in the remaining graph. So what this achieves is this independent set, by definition, has no induced edges in it, and that's conducive to maintaining stability. So what I mean by stability is, suppose we let everyone in the IS play 1 and everyone else play 0. The resulting configuration will be stable because there's no pair of neighbors who are both contributing. But the problem with this is that it could be inefficient. So there's no bound on the size of IS as a function of opt. So what do these mean if we go back to the double star graph? The dominating set will just be the two centers. And after removing them, the resulting graph are just isolated nodes, so that the independent set is just the remaining nodes. And we saw earlier that on the double star graph, we could just randomize between those two situations. And this is also true in general for general graphs. So that is how we describe the proof in the paper, but that's not entirely what's happening. So how we actually got the result was by noting that the problem is just a linear program. So suppose we fit the space of all signal values. We can just predict one of the m fixed values. Then a signal stream is just a distribution over the possible combinations of signals. And there are just m to the n such combinations, so it's a high-dimensional vector. And with this in mind, the condition of persuasiveness just reduces to linear constraints. So we call that persuasiveness says for any of the signal values, we have certain identity. And if we write this identity in terms of p, that becomes a linear constraint. And finally, the objective of minimizing the expected cost is also a minimization of a linear function in p, because that's how expectation is defined. So the conclusion is we can just compute the optimal Bayesian persuasion stream. Suppose we know the signal space using a linear program. But this simple observation doesn't give us anything immediate because it's not an efficient algorithm. It has an exponential size. But we can use this to guide the proof of upper bounds and lower bounds, because upper bound will just be finding feasible solutions to the LP, while lower bounds are finding solutions to the dual LP. And what's more important is that this allows us to solve the instance numerically on very small graphs, like we generate small double star graphs and guess the solutions. So essentially, this is all done by some street fighting mathematics. So if you haven't heard of the term, there's a nice lecture by Ronaldo. It basically says, if you want to solve a general problem in general n, and you don't know how to solve it, just solve it for small values of n and look at the pattern, or use some certain resource to guess the pattern. So I should mention that this is sometimes viewed as an unorthodox style of problem solving, because if you have perfect intuition, you don't need this. We just get the theorem and get the proof. But personally, I found this very useful in this project. And this already feels pretty outdated from today's standards, because we did this in 2023, 2024. So we did the coding and looked at the pattern by hand. But now a lot of these things could be streamlined by those powerful AI models. So let me summarize and talk about a few open problems. We saw that efficiency and incentives are at odds, even in very stylized, simple models of collaboration. We saw this linear price of stability in double star graph. And Bayesian persuasion offers a solution to the problem. We can reduce the POS to sublinear in n in various situations. So what's next? So my claim is, even in this current model, there are interesting questions if you are expert in game theory. So one recurring theme in our work was that simple streams are effective. By simple stream, I mean that streams that only uses 2 or 3 or constant number of signals. So we saw this for the double star graph. There's just 1 minus epsilon or 0 as a signal. So one conjecture would be that these signals are sufficient, not only achieving a worst case analysis optimality, but also instance optimality. And we showed that this is not true for if we require exact optimality. So we can construct instances on which at least 4 signals will be needed, but it doesn't say anything about approximate optimality. And another good thing about simple models, simple streams, is that they are conducive to efficient calculation. So I mentioned earlier that the size of the LP is exponential in the number of n, in the number of nodes. But if we really look at the LP, we can further reduce the number of variables to just polynomial in n, assuming a small signal space. But the hurdle here is that finding those poly n variables requires solving hard graph problems. But I'm still pretty optimistic that we can at least get, say, constant approximation using a polynomial time algorithm. And take one step back, as I mentioned throughout the talk, there are definitely many ways of refining the model. So one element is a learning model, where we can replace the graph network with certain stylized learning tasks like mean estimation or linear regression that are well understood. Another idea is to use those empirical scaling laws or recent theoretical results on universal learning curves to get more refined models of how learning works in this collaboration. And also, what I mentioned in the talk, we're implicitly using a specific utility model that's penalizing both deficiency and surplus in the data. But there are definitely refinements to this where one can be, those two should be penalized in an asymmetric fashion. And finally, there are other relaxations of the Bayesian persuasion model, which should be conducive to handling the nonlinear case that I mentioned earlier, or get even simpler proofs of our results. So that's all I have for today, and thank you very much for listening.
We have time for a few questions.
Thank you. So I have two questions. So it seems like you model the unknown's position in the graph by doing permutations, and that kind of seems like taking a uniform distribution over where you are in the graph.
Yes.
What would change if you had different probability models over where you are in the graph? I think I'm more likely to be on the center or the edge, because at one extreme, when I know with probability 1 where I am, it seems to collapse. But on the other extreme, it seems like it's this random permutation. What happens in the middle?
That's a great question. So we consider a slight, so everything still works if the permutation is not uniform, but the marginal is uniform. But we haven't really thought about this non-uniform case. I would guess some smooth analysis type analysis should work by looking at how different the maximum mass on each possible location. I would expect something of that sort to be true.
I see. And then the second one is, have you thought about a model where the graphs evolve over time? I can imagine that because data is freely shareable and replicable, then maybe I receive some data and now I have that and then I could give it to someone else.
Yeah, I think that's a great extension of the model. I think one kind of strange thing or critique of the model is that it's not ex post stable. You get the configuration, you realize what your neighbors are doing, and then you realize you're not really you might get a deficiency or surplus in the realized situation. And I think what you suggested would be a nice way of extending this in an evolving environment.
Thank you.
Other questions?
So I like the theoretical model, and it's very nice, and the math is brilliant. I'm wondering, towards the application of sharing data, how applicable is this, and what are the features that are kind of most true to reality, and what are the features that are maybe slightly artificial?
I feel that I'm not familiar enough with what's happening in practice to say anything meaningful about this.
Thanks.
Any last question? Okay, well, thank you, Mingda. Okay. Our next speaker, now